LPFF, a portrait dataset for face generators across large poses. In this paper, we present LPFF, a large pose Flickr face dataset comprised of 19,590 high-quality real large pose portrait images. LPFF can help 2D face generators extend their latent space and better manipulate the large pose data, and help 3D-aware face generators achieve better view consistency and more realistic 3D reconstruction results. Now we introduce our motivation. Generative adversarial networks can achieve 2D high-resolution image generation, and accomplish a variety of downstream image editing tasks, particularly face modification. 3D-aware generators can describe and represent geometry in their latent space while rendering objects from different camera perspectives. However, both the existing 2D and 3D approaches are unable to process large pose face data. Regarding 2D face generators, those large pose data are outside of their latent space, causing at least two problems as follows. First, moving the latent code along the YA pose editing direction will cause it to reach the edge of the latent space before getting side faces. Second, it is challenging to project extremely posed images to the latent space, let alone performing semantic modification on them. 3D-aware generators achieve excellent image synthesis performance on faces in small to medium poses but have obvious artifacts at steep angles. The issues in the face generators are mainly caused by the unbalanced camera pose distribution of the training dataset, FFHQ. To analyze the camera distribution in FFHQ, we convert all the camera parameters in FFHQ into theta and phi angles. It can be seen that large pose face images are scarce in FFHQ. As a result, face generators cannot learn a correct large pose face distribution without sufficient large pose data. In order to improve the performance of face generators, we propose a novel high-quality large pose face dataset. Now we introduce our data processing pipeline. We first collect raw portrait images from the Flickr website. Given a raw image, we first use delib and face alignment to get its 68 landmarks. Then the 68 landmarks are used to get the realigned image and the 5 positions of the eyes, mouth, and nose. After that, we use the face reconstruction model to extract camera parameters and the landmarks of the reconstructed face. We then manually remove any instances that are incorrectly reconstructed. Then we use the landmarks of the reconstructed face to get final images according to EG3D functions and style-GON functions respectively. In order to only collect those images that are at large poses, we first compute the density function of the camera distribution of FFHQ. Then we filter the images with a density of no more than 0.4. Finally, we get 19,590 large pose and high-quality face images as our LPFF dataset. We combine LPFF with FFHQ and get a dataset with 89,590 images. Compared to FFHQ, our dataset has a wider camera distribution. In EG3D, to increase the sampling probability of the low-density data, the authors rebalance the FFHQ dataset. Inspired by EG3D, we also rebalance our dataset according to the data densities. Please refer to our paper for more details. Now we introduce our training details. Regarding the 2D generator, we retrain style-GON 2 using our dataset, then fine-tune the trained model using our rebalanced dataset. As for EG3D training, we first use our dataset to train EG3D from scratch. We then fine-tune the retrained models using the rebalanced dataset. We also fine-tune the retrained model by conditioning the generator using the average camera. Now we present our evaluation results. We compare the pose distribution of the latent spaces by displaying the results of linear YA pose manipulation. As for the model trained on FFHQ, the side face results are far from a genuine human face. Our models produce reasonable large pose portraits. The comparison shows that our model's latent spaces are more extensive and better able to present large pose data. We project large pose portraits into the latent spaces of those models. The models trained on our dataset have fewer artifacts and can better represent the large pose data in latent spaces. We apply semantic attribute editing to the projected latent codes. This is another semantic editing example. Now we demonstrate the performance of 3D-aware face generators. We provide the samples generated by the models trained on our dataset. Even in large poses, our synthesized images and 3D geometry are high quality. Now we show the comparison of multi-view synthesis results. The two presented models are trained with the same training strategy but using different datasets. The two models both achieve high-quality image synthesis performance on faces in small to medium poses. But when rendering from large poses, the model trained on our dataset outperforms the one trained on FFHQ. The two presented models are trained with the same training strategy but using different rebalanced datasets. The two presented models are trained with different training strategies and different datasets. To evaluate the ability to fit multi-view images, we use FaceScape as the testing data. We use 4 multi-view images of a single identity as the reference images. We perform latent code optimization to project the identity into latent space. Then we render novel views for the reconstructed face. We also perform PTI inversion to single-view testing images collected from Unsplash and Pexels. The results of image inversion reveal that our models produce reconstructed face geometry with fewer artifacts, thus suggesting that the learned 3D prior from our dataset is more realistic. Thank you.